have to do any tricks. But this is when you, this is where you know you can't solve it, right? You probably can't solve it in the amount of time you have. Then what are you going to do? You have two choices. You could leave it blank, or you could start thinking, are there any tricks to make it easier? And yeah, there are tricks to make this easier. One trick to make this easier is to use the simplifying assumption. And so the book, you know, this is in the book actually, but they don't solve it all the way. So one of the tricks they do is use the simplifying assumption that's going to get rid of this, and it's going to get rid of, actually it's just going to get rid of this. Right? Okay, and then you know what? They do a new trick, a trick that I haven't talked about. You know, a trick you've probably never done, because when you've done these two equations, two unknown, you solve for either x or you solve for y. But the trick they do is they don't solve for x or y, they solve for x plus y. So they solve one of these equations for x plus y and then substitute, and then it makes it a heck of a lot easier. So that's a trick that you probably didn't have up your sleeve, but that they used, right? And so these little tricks you do because you get stuck. This is when you know you need to use them. Otherwise, you don't have to use them. If you can solve the problem, just solve it, right? So this is why I wanted you guys to try this, because, you know, a lot of people, if I give a simultaneous on the exam and they want to get the bonus, because you don't have to solve this to get you just set it up and say you got to solve it simultaneously, you'll get full credit. But some people want to get the bonus because they have some time, and so they try to solve it. So I just see a lot of algebra there, but no answer. You know, they just, and then sometimes I see a lot of algebra and the answer. You know, but that's not the only tricks you can use. You know, there are other tricks you can use to solve this. And so that's why we have these. I don't know, maybe I shouldn't call them tricks. What should I call them? Like, techniques you can use to solve these things. You know. And these techniques, you know, it's like this. You know, you don't have to learn these techniques if you just stay with problems that are simple to solve. But when you get into more complicated problems, you have to learn it. And do you want to stay in a little, you know, isolated, like, okay, these are the only problems you're going to be assigned, the ones that work? No, because in real life, of course, it's going to be much more complicated. And so, anyway. So we tried lots of things like resetting, et cetera, et cetera. You know, because if you did Le Chatelier's, oh boy, you're in for a headache. If you did Le Chatelier's here and called this 1.0 times 10 to the minus 7 molar plus, you know, y, and then it's going to be, or actually it wouldn't be, this would be Le Chatelier's, it'd be 1.0 times 10 to the minus 7 molar plus y molar, giving you that, and then minus x, and this is a big headache. And so we do lots of little things to do it, but you know, since there's so many variations, it's easy to get mixed up, and it's easy to use two different ones, which
When you say solve for x plus y, I tried that, but it still end up with the equation that has x and y in it.
yeah, we'll solve the other equation for x and y. We have two choices to solve. You could solve this equation for x plus y, or you could solve this equation for x plus y, and then substitute. So which one did you solve for x plus y?
I solved the second one.
You solved the second one? Solve this one for x plus y, and then substitute it.
I solved the other way. I solved the top one for x plus y, and I still got some funky stuff.
You still get some funky stuff. All right.
So we would have to use simplified assumption for the top one? And the y one?
Yeah, you could use a simplifying assumption. So one of the things we'll do, let's just look at this one here. Let's do this one. Okay, so if we assume the simplifying assumption, then we'll just assume that y is much smaller. That's a reasonable assumption because the k is quite small. although the concentration is very low, so the simplifying assumption might not work in this case. But we might as well try it and see later if it worked or it didn't work. And so what we're going to get is this. We're going to get x plus y times y divided by 1.0 times 10 to the minus 5 and then we'll solve this one. We get x plus y is equal to 6.2 times 10 to the minus 10 times 1.0 times 10 to the minus 5. So this is going to be plus 5. So this is going to go to 6.2 times 10 to the minus 5 divided by y. So let's make that. So that's what you got? And then substituted it? All right, so we substituted back in here, and we're going to get a x and y. You're right. So this is going to be a problem. All right, then we try the other one. So we try the other one, and we get x plus y is just going to be this over x. And then substitute it here, and we're going to get x and y.
Well, I solved the y for the second one, and I get all the x's in one equation only.
In one equation only?
Yes, but it's really complex.
Okay. So,
So even how we solve it,
yeah.
it's like
So this one, let's see what the book did. They actually don't solve the whole thing. They just tell you. I've solved this one, but you know what you have to do? You have to do another trick. It's not really a trick, but what's the other trick? Successive approximations. So we have to do successive approximations to complete the solution. But let's see. The book uses x plus y, but I haven't. We could solve it for y. That's weird. There's one more assumption that we need to make than in solving this. But anyway, let's do this. What was the equation that you ended up generating?
So for x going around 1.0 is 10 to the number 2 over x. I just,
For the second one?
yeah, I just saw the second one.
All right. 1.0 times 10 to the negative 14 over x. Okay. And then we substitute it up here, and then we get x and y again.
Yeah.
Yeah. All right, so then we have to do something else. Otherwise, we aren't going to be able to solve this. What else can we do? Because obviously both of them are going to yield x and y. Right? And then you solve it for y. And so what we could do is we could solve one of these for one of the variables and then figure out the other. But before I do that, let's see what we end up with here. And so if I substitute it up here, we're going to get 6.2 times 10 to the minus 10 is equal to 1.0 times 10 to the minus 14 divided by x times y. If we substitute it down here, we'll get get 1.0 times 10 to the minus 14, and x plus y, 6.2 times 10 to the minus 5 over y times x. And so neither of those worked. So we have to have some other assumption that we make, or we don't. Actually, I don't usually solve this x plus y. I usually solve this with a single variable, but
Just do it your method.
yeah, let's just do my method. All right, so for this, we could solve either for x or for y, but both of these are going to be kind of complicated. And so which one would be easiest to solve here? The bottom one? Actually, the bottom one, even though it looks easiest, is, remember, not so easy. All right, so let's solve this one for x. If we solve the bottom one for x, then we'll get x is equal to 1.0 times 10 to the minus 14 divided by x plus y. Okay. And then we could try to substitute it in, and we get the same thing. So x plus y is going to give us All right, so I'm in the same boat you guys are in, so I got to figure it out. It's been a long time since I solved this, so I just remember grinding through a lot of math.
You solve the y on the second one.
If we solve for y on this second one,
And then got all x's.
and we get it all x. All right.
Just for all of it.
So this is going to be x plus y is equal to 1.0 times 10 minus 14 divided by x. And then solve for y. Y is equal to 1.0 times 10 minus 14 divided by x minus x. And then substitute it in here. So we will get 6.2 times 10 to the minus 10 is equal to
It should be minus x squared, right?
x plus y, 1.0 times 10 to the minus 14 minus x over x. Okay. And then 1.0 times 10 to the minus 14 over x minus x. And then 1.0 times 10 to the minus 5 minus 1.0 times 10 to the minus 14 divided by x minus x. All right, then what?
Then use the successive approximation.
We could try successive approximations.
We are allowed
So if we use successive approximations, what should we guess? as our x value. I would probably just leave it like this, maybe, rather than multiply these out. This one, probably leave it. You can't really cancel. These don't cancel because this is a subtraction here.
No, the top one is not x plus minus x.
Oh, you mean this x, yeah. Okay, we can cancel those out. The common denominator of x squared.
Because it's x, right? So minus x would be x squared or x, but that was.
Yeah, you could do that. But for successive approximations, do we have to change it? No. Do you guys have an invert key on your calculator? Or just actually invert key? You don't really need it. We could just do the division.
So you lose the 0.
So what are we going to do for x? So what should we guess for x? Well, x is going to be the hydronium from water, right? So the hydronium from water is going to be, what's the most hydronium you can get from water? Yeah, because the situation here is the H2O liquid plus H2O liquid. If there was no hydronium present here to begin with, that is, we just reset it to 0 and 0, then the maximum hydronium we're going to get from pure water is going to be 1.0 times 10 to the minus 7 molar. This is going to be 1.0 times 10 to the minus 7 molar. And so this is the max. But if we have some common ion present, that is, we have Y present, you know, we aren't going to generate as big of an X here because of the common ion effect. And so the change here is going to be a much smaller X, plus X molar here, plus X molar here. And so at equilibrium, we're going to have Y plus X molar, and then X molar here. And so in this case, X has got to be much smaller than 1.0 times 10 to the minus 7. That's what it's got to be. And so, you know, our first guess, we could try 1.0 times 10 to the minus 7, but it's going to be too big. So what should we try here? And so we would just guess a value of it. What we could do is we could just try to guess a value of, let's just make it an order of magnitude smaller, 1.0, or just, we'll get rid of the 0.0 so we don't have to punch in as much. We'll just try 1 times 10 to the minus 8. And then see, you know, how close we get to 6.2 times 10 to the minus 10. You could see how the book solved it here on page 715. But what does this come out to? Here.